Hello everyone, now I am going to introduce the software of SpinQ Gemini LAB. As you can see, the interface is made up of 3 sections, which are the experiment section, equipment section, and user settings section. In the experiment section, we can explore experimental guidelines and access the experimental modules to conduct experiments. After turning on the computer and before we start running an experiment, users need to do a few steps to ensure robust experimental outcomes. Clicking the equipment section, we can monitor the status of Gemini LAB, such as temperature, magnetic field, and the change of resonance frequency of qubits. Based on this data, users can determine if the quantum computer is working well or not. If not, we can use the auto-calibration functionality, which will take about 5 minutes. If there is a significant change in the magnetic field, we can use the auto-shimming functionality, which will take about 30 minutes. For general users, our automatic functionalities are enough to meet requirements. However, for more detailed and precise debugging, engineers can click the setting button at the bottom right corner of the interface to test the equipment in more detail. The user settings section includes functionalities such as authorization, user settings, and more. Let's get back to the experiment section, consisting of 4 modules. The Principles of Quantum Computing module is the most fundamental and required. We also have 3 optional modules: quantum algorithms, integrated quantum technology, and research experiments. You can choose based on your needs. Let's take the first experimental module as an example, to showcase how they can serve you in quantum computing education. The Principles of Quantum Computing module consists of 9 experiments, breaking down the underlying principles of quantum computing into 9 individual experiments. Each experiment is equipped with corresponding guidelines covering the principles, step-by-step instructions, and more. Following our detailed guidelines, users can conduct experiments, record the experimental data, and write experiment reports. For example, in the first 4 experiments, users can observe phenomena including spin magnetic resonance, Rabi oscillation, quantum superposition, and quantum decoherence, and measure important parameters related to the quantum system. These measured parameters can be applied in subsequent experiments. In the following experiments, users can gain hands-on learning of how to effectively control the quantum system, how to initialize the quantum system, how to construct quantum gates in quantum circuits, and participate in the data processing of quantum tomography. Finally, we can conduct a complete quantum computing task using the hands-on knowledge we gained from SpinQ Gemini LAB. The first experiment is the NMR phenomenon and signal. Spin resonance is the foundation of all quantum information technologies and quantum computing technologies based on spin manipulation. In this experiment, we can learn about the principle of nuclear magnetic resonance (NMR) through studying the experimental manual. Then, according to the experimental steps, we can observe the NMR phenomenon, understand the process of free induction decay (FID), and measure the nuclear spin resonance frequency. Firstly, at the bottom left of the interface, we can enter an interactive animation interface through the Principle Explanation button and understand the physical image of nuclear magnetic resonance intuitively. According to the principles and values given in the experimental manual, we can calculate the approximate resonance frequency of the nucleus and try to excite the atomic nucleus by emitting a radio frequency field. Press the pulse setting button at the bottom right to enter the pulse setting interface. In this interface, we can set all parameters related to the radio frequency pulse, such as radio frequency, detuning, phase, amplitude, pulse width, etc. Meanwhile, we see that there is a function similar to an oscilloscope at the top of this interface, where we can visually observe the waveform of the radio frequency field. By continuously adjusting the frequency of the radio frequency field, we can eventually excite the atomic nucleus, thus observing the free induction decay signal emitted by the atomic nucleus and the corresponding frequency domain signal. We accurately obtain the resonance frequency of the atomic nucleus through the NMR phenomenon. Click Lock to record the obtained atomic nucleus resonance frequency, and continue to use the resonance frequency parameter in subsequent experiments. In addition, we can observe the changes in the atomic nucleus resonance frequency in the equipment monitoring interface, and these changes occur with the environmental magnetic field. By using an external small magnet to interfere with the main magnetic field in the device, we can see a noticeable offset of the nuclear spin resonance frequency as the environmental magnetic field changes, it proving the impact of the external magnetic field on Zeeman splitting. The next experiment describes Rabi's oscillations. In this experiment, we observe Rabi oscillations by continuously applying a radio frequency field to the nucleus based on the resonance frequency of the nucleus measured in the NMR phenomenon experiment. This is used to understand the energy level jumping behavior of the nucleus and to measure the parameters of the Rabi oscillation frequency that will be used in subsequent experiments. The Rabi oscillation experiment is important in quantum information technology because it is the basic method of controlling qubits. Similarly, we can familiarize ourselves with the physical image of Rabi oscillations through the interactive animation on the principal explanation page. The continuous application of a radio frequency field causes the state of the nucleus to continuously flip, which is the process by which the nucleus undergoes a jump. Then, we edit the experimental parameters we need in the pulse setting interface and interact with the quantum system through the radio frequency field. According to the content of the experiment, different excitations of the nuclear spin are performed and different experimental data are collected. In this process, we can see the free induction decay signal and the corresponding spectrum data of each experiment on the interface. With the button at the bottom right corner, we record the collected data points in the chart on the right side. This chart can be deleted and edited. Afterward, we fit the data points on this chart to the data to obtain the Rabi oscillation pattern and the Rabi oscillation frequency. The quantum bit experiment is now introduced. Quantum bit, short for qubit, are the central element of quantum computing. This experiment uses nuclear spin as a quantum bit and explores its quantum mechanical properties. First, in the principal explanation interface, we can understand the difference between the microscopic magnetic moment of the nucleus and the macroscopic magnetic moment, as well as the physical model of the qubit. Then we will experiment according to the contents of the lab manual. Based on the parameters of Rabi frequency measured by the Rabi oscillation experiment, we can perform some specific operations on qubits in the experiment to observe the different properties of qubits from those in classical physics. The raw data of the experiment is displayed on the left side of the interface. On the right side are the graphical results obtained from the processing of the raw data, including the block sphere, the nucleus superposition schema, and the wave function-related graphs. These graphical representations of the experimental results provide a multidimensional view of all the state parameters of a qubit. Next, let's introduce the quantum decoherence experiment. It is important for quantum computation that qubits maintain coherent properties. In this experiment, we will observe how a qubit backs from a coherent quantum state to a classical thermal equilibrium state. We will also measure important parameters related to the decoherence process. First, we can learn about the physical image of quantum decoherence through an interactive animation. Next, arrange reasonable experimental operations according to the content of the experimental guide, stimulate the atomic nucleus for feature excitation, and observe its decoherence process. We can see the raw data of the experiment in the upper left corner, the block sphere of the current state of the qubit in the lower left corner, and the density matrix of the quantum state next to it. We can see that after a series of experimental manipulations, the qubit degenerates from the surface of the block sphere to the interior of the block sphere, which is an obvious relaxation phenomenon. In the process of multiple sampling records, you can get the trend of the change of the relaxation of the qubit graph showing on the right side. Through fitting the data on the graph, you get the decoherence time constant. We can manage the data on the graph and can change the fitting model of the data and different data processing for different experimental data. The experimentation on quantum control lies at the heart of quantum computing. In previous experiments, users gathered data on quantum system parameters and grasped principles of governing qubit manipulation. Following the experiment manuals, users can operate many important quantum controls by controlling the parameters of the quantum system. These include single qubit rotations around arbitrary axes and the evolution of coupled two-qubit systems, laying a foundation for constructing quantum logic gates. The interface presents raw data on the left-hand side, processed visualizations of quantum states and density matrices on the right. These demonstrations enable users to observe the varied effects of different quantum control ways. After mastering quantum control techniques, users can subsequently prepare for the initialization of the quantum system. Before processing any information, a quantum system should be initialized to a certain state to ensure coherence in data processing. In this experiment, users transition the quantum system from a state of thermal equilibrium to its ground state by quantum control techniques, laying a foundation for quantum computing experiment. Furthermore, users have the flexibility to apply their custom quantum system to forthcoming experiments. The experimental outcomes of quantum system initialization are presented in raw data, energy level distributions, and density matrices. Next, we introduce the experiment on quantum logic gates and quantum circuits. Quantum logic gates are the basis for information processing in quantum computing. In analogy to classical computers, we first need a universal gate set to perform any logical operations, and only then can we implement more complex algorithms. Therefore, in this experiment, our aim is to construct a universal set of quantum logic gates using quantum control methods. We can see the truth table for each quantum logic gate on the left side of the interface. Clicking on the list, we can switch among all common quantum logic gates. After that, we can build the corresponding quantum logic gate by setting the experimental parameters. We can test quantum control. And the test results will be displayed in the experimental data on the right. Based on the test results, we build the quantum control sequence into the quantum logic gate we want to use. After building quantum gates, you can view and modify the parameters of the quantum gates or save them. The quantum logic gates built here will be used in subsequent experiments. Entering the quantum circuit interface, we can choose not only the initial state and quantum logic gates we have set before, but also select built-in parameters. According to the requirements of the experiment manual, various quantum circuits can be built here. The operation results of the quantum circuit will be presented in the form of density matrix and graphics. The left side shows the experimental results, and the right side shows the reference results. The quantum state tomography experiment is introduced next. The quantum state tomography is the operation of reading out the end state of qubits obtained by quantum computation. We will perform the experiment based on the quantum logic gate constructed in the previous experiment, and then participate in the quantum state measurement readout operation. After choosing the built-in or customized initial state and quantum logic gate, by designing different readout operations, we can get the quantum state's different raw data. By fitting the raw data, we can obtain the angular momentum information embedded in the raw data of the quantum state. Based on the calculation of the angular momentum information, the quantum state tomography is finally realized and verified in the tomography interface. The interface will give the fidelity of the user's measurements and the theoretical expectations. The quantum computing task is introduced now. Based on all the teaching experiments mentioned above, we have mastered the underlying principles of quantum computing and constructed the initialization process and quantum logic gates necessary for quantum computing. Next, we will integrate all the contents to carry out a real quantum computing task. In this experiment, we have the same choice of parameters built into the system or those constructed by the user in the previous experiment. The top half of the page shows the quantum circuits, while the bottom half shows the various parameters of that quantum computing task. First is its underlying parameter, which is the pulse parameter corresponding to each quantum logic gate. After that, we can also see the raw data corresponding to all the different readout operations of that task. It is also possible to see the experimental results of the quantum circuits as well as the theoretical expectations. Finally, there is an experimental evaluation of the quantum computing task, which includes the experimental fidelity, the purity of the quantum states, and various details related to the experiment. In this experimental interface, we will utilize the quantum computing task to perform a complete experimental case as provided in the lab manual. The results of this task will be evaluated.